Welcome everyone. This is computer vision. In this fourth lecture, I'm going to show you histogram-based detection and tracking algorithms. We are still in the conventional computer vision block, so 3 more lectures to go until we then switch to deep learning. In the first half of the lecture, I'm going to present CAMSHIFT to you, which is an algorithm published quite a while ago by Gary Bretsky, who works with Intel, and which was one of those algorithms that was shipped with OpenCV, an open source computer vision library. CAMSHIFT is fairly simple, runs pretty fast on today's computers, and can be used to track faces like here, or really any object that has color. So in the very first lecture, we discussed using region in our favorite color space, and then look up for every pixel in our input image whether that specific pixel belongs to the positive subspace, and then use that to binarize the input, and then post-process this binary image to then, find the position and also the bounding box of the object in question, or the object to be tracked. Now, today we're going to advance that concept a little bit because now each of the input pixels receives a probability to belong to an object, and that probability is estimated by a histogram of a given template. So before we start explaining how this algorithm works, let's introduce histograms. So histogram is, comes from Greek histo, I think it means bar or pole, and gram, I think is like a chart, let's say, and I think it comes from English even. So it's a bar chart, yeah? And so color bar charts now take in an image, and we want to count the different colors or the pixels with a different color, for example, orange or yellow or green or blue. So a histogram is how many of these pixels for a given color we can find in an input. So let's say we would order the colors from red to blue. We would have like 6 pixels with the color orange, 1 pixel with the color yellow, 3 green, and 6 blue pixels. Okay, that's an histogram. Now we introduced color with 3-dimensional color spaces like RGB for red, green, and blue. And so each pixel has 3 values for these 3 dimensions, and so every pixel can be thought of to be positioned in that 3-dimensional space for its color. Now, 3-dimensional color histograms therefore need to use that 3-dimensional space as well, right? So you can think of each of these regions to have many of these dots, so many of these pixels with a certain color, or like in some regions there's practically no pixel that has this specific color. So we do not want to do 3 one-dimensional histograms, for example, for all the red values in green and blue channels. Although you will see this, for example, in paint programs, paint softwares, that give you a notion about how strongly a certain hue, like a color hue, is in the image. So for the idea that I'm going to present to you today, we would actually need a 3D histogram. So we would have 3 dimensions, R, G, and B, and we would take all the input pixels one by one, and for each of these colors we would index into the structure and increase a count so that in the end we have a 3-dimensional histogram. Now, we will not use this. So why do you think that is? So what is the problem with a 3D histogram? So we'll discuss those those problems or the answers to these problems in the Q&A session on Wednesday. For now, we decide that we want to use a different color space, and we decide for HSV, which is short for hue, saturation, and value. Again, 3 dimensions, and we can represent color now as hue, so that 1 dimension, which is like a radial and angular dimension that starts at 0 degrees, which is red, and then turns to green, blue, purple, and then back to red. You can find the exact conversion equation on Wikipedia, but for now, just to explain how that color space is motivated, it kind of models how color or material that has color appears when you shine light on it. So that's the value dimension. If you have more light, the color appears much more intense, and the less color you shine on it, the darker and dimmer it gets. Yeah? Saturation now is maximum, or with maximum saturation, colors appear purest, right? And the less color you add in this mix, so you can think of like tinting it with white, with color white, it like fades out, so that here in the center axis you have a gradient between white in the top and black in the bottom. Okay, you can read about that on the link shown below. And now the HSV color space allows us to create one-dimensional color histograms. So for that input image here, we count how many hues, right, different hues there are. And remember now, for example, for that orange hue here, there may be pixels that appear less bright because the value, the brightness is lower, or a little faded out, like only half saturated or so. They still will be counted in that bin. Now, again, the idea today is that we'll use the color histogram to describe an object that we want to track. So let's say we want to track my face in a video. We compute the hue histogram, the color histogram of that region, and it looks like that, right? So my face is, mostly orange. A little bit of blue is in there, and a little bit of purple or red. And then we'll use that as an object descriptor. So for each pixel in the new input image now, we'll look up how many of these colors we had in the object description in the template. So for example, a pixel here on my forehead indexes into that color, and then we see, oh yeah, that was pretty frequent in the template, and then we replace or we write that value here in a new array, in a new image, such that if we do that for all the pixels, for all the colors that we find, we will receive an image that looks like that. Yeah, so, and because the object's template, my face template, had many of these like flesh or like skin colored hues, the region that covers or that corresponds to my face and my neck is pretty white or pretty bright. Okay. So, and now we basically just have to find the position and maybe the spatial scale, and then later the orientation of this blob here. Okay, and we will do that, and the paper also does that, using an algorithm that is already known quite a while ago. It's called mean shift. So the idea is that, given a probability distribution, and a search window, the problem is where is the center of the distribution, and we'll do that by computing the mean in the window and shifting the window position onto that mean, and magically we'll walk up that distribution. Yeah. So for this given window, the mean of these, or the weighted mean of all the positions here, weighted by the underlying distribution, is this blue dot. Now, if we then move the window on that position and then compute the new mean, the new average, the weighted position, we see that it nicely walks up that hill. Okay, so formally we can use so-called image moments. These are defined with this m here. So m00 is just the double sum over all x and y values in that window. And we sum up all those underlying image pixels. So let this image I here be the probability distribution. And we call that the 0th moment, which is basically the sum of all those values in that image, or in the region. Make sure you have centered coordinates. Yeah, so in the center of the image we have x and y equals to 0, 0. Okay. Now there first order moments, m10 and m01. And it reads very simply, double sum over x and y, x times the underlying image, or y times the underlying image. Yeah? So that's basically, we give a weight to all the x coordinates, irrespective of y or irrespective of x for the y's. Okay, and we can also introduce the center of mass now using those image moments. Okay, and so the question would be, show that is actually the center of mass. In your assignments, we will first ask you to read the CAMSHIFT paper. We will then ask you to implement an initial search window to extract an object's hue histogram. You have to then implement this probability image like I showed you before, given that histogram descriptor, and then track the mode, so the position of the color distribution, the average position of the color distribution with mean shift. Okay. Now, what happens if we lose track of the object, right? So let's think of me having moved to the side, and then the search window is not overlapping with the target distribution anymore. Actually, here the mean that we'll compute will probably move outwards, so away from the face. So how can we make sure that we'll not lose track? Okay, so one of those answers that I expect you to give is that we can have an adaptive window size. So grow the window when there's enough probability mass. So we would have a harder time of actually losing the distribution, although that wouldn't make it impossible to lose it, but that would counteract some reasons why we would lose the probability distribution, because the window was so small. Yeah, and that is a figure from the paper. The window size here is represented by this yellow window, this yellow function. And you'll see over the steps, it kind of grows and adapts to this object here. This is just 1D, right? And they propose using that small equation here. So S, that's the window size. Let's think of this as the width and height of a quadratic search window. And that's just a function of the 0th moment, so the actual sum of probability mass divided by a constant. And then since this is a function of the area, we then use square root to have something that relates to the width and height. Obviously, this is something that people just heuristically found. I think there are a couple of more ideas that we can implement to have an adaptive search window. Yeah, so for example, one of those questions would be, what happens if you have like a non-zero noise level? Okay, now the paper also proposes tracking not just the position and the size of the object, but also the orientation. Yeah? And we'll do that by using this monster of an equation, although if you look at it, it's pretty simple, and also Wikipedia here shows you how to simplify that equation. What I want you to do is look at this closely and read also that article, because it actually extracts the first principal component, so the main axis of this probability distribution. And there are different ways to write that down. So you could compute the covariance matrix, and then take the eigenvector that corresponds to the largest eigenvalue. But you can also access that property without an explicit computation of the covariance matrix of these points, using the formulation you can find here. Okay. Now your second exercise on the current assignment will be to implement this automatic determination of the search window, and implement also the extraction of the object orientation. And to show us that it worked, you have to draw an ellipse, whose main axis and orientation is determined by those two parameters. Okay, let's summarize color-based object detection. First of all, color can be a stable feature. Depending on a variety of factors like scene lighting, camera pose, object material and reflectiveness and all these things, you may get a lot of variation in color space. And using HSV, for example, or other color spaces that model different aspects of your scene can help. And we saw how HSV can be used in contrast to using RGB. Color, though, does not encode any structural image features, so you are going to have a hard time discriminating between different objects and have the same color or the same color distribution. Now, today we saw how color histograms can actually serve to describe an object, and how we can then use this description, this histogram, to produce a probability distribution that describes, for each pixel, the probability to belong to the described object. And then as this distribution can then be post-processed, look at mean shift and the way we compute the scale and the orientation of the probability distribution, we can then use this to track an object. But even in HSV, it is not perfect, right? Color may still vary depending on a variety of factors. So be aware of the limitations of color-based object detection. Okay, so that was color and color histograms. Please collect your answers for the questions I posed and other questions for understanding that deeper. See you on Wednesday.